Hello everybody. In this video, we will see the solution of Aerospace GATE 2021 questions related to the topic propulsion. So without further delay, let's get into the first problem. So first let's write what is given in this problem by going through the problem. So let me put what is given in the problem. So an aircraft with the turbojet engine is flying at a velocity of 270 meter per second, which means that what CA, the axial velocity, the velocity at which the flow is coming into the engine is 270 meter per second. So which is CA we generally call, right? In terms of propulsion world, the axial velocity is called CA. The enthalpy of the incoming air at the intake is 260 kilojoule per kg. So which means that the enthalpy is nothing but the HI. So incoming, I stands for incoming or the inlet, and the enthalpy is given to be 260 kilojoule per kg. And now the enthalpy of the gas at the exit of the engine, which is nothing but the nozzle. So HE is equal to 912 kilojoule per kg. Now the ratio of mass flow rate of fuel and air is equal to. So they have given the ratio of fuel m dot F by m dot A is nothing but 0.019. Okay, the chemical energy of fuel is, so when you add fuel in the combustion process, right? So the chemical energy of the fuel, which is given as QR, generally we denote the chemical energy to be QR, equal to 44.5 megajoule. Okay, it's not kilojoule, megajoule per kg. So now and they have told the combustion process is ideal, which means there is no loss or something like that. So the total loss of heat from the engine to the ambient, so there is some total loss of heat from the engine to ambient. So the heat loss is nothing but, which is given in terms of Q. I have put L. The amount of heat generally we denote as Q. L is considered as loss. Okay, the heat that is getting lost in this process, which is nothing, basically the loss, which is nothing but 25 kilojoule per kg. The velocity of the exhaust jet is, so the velocity that is coming out of the nozzle. Generally, the exhaust jet is called as CJ. Okay, they have asked what is CJ. Now let's try to understand in a schematic or a diagrammatic way. If this is the way the engine looks like, right? And this is the inlet, and let's see, this is the outlet. Okay, so this is nothing but CA, and the velocity that is asked in the question is CJ. So this is what is asked in the question. CA is given, and so mass flow rate is m dot A, which is going in, and m dot will get added here, right? The fuel will get added here, right? M dot F, which is the fuel, will get added in the combustion process, and the amount of heat that is getting lost out of the engine is QL. So which is this one, 25 kilojoule per kg, that is getting lost, and the fuel heating value of the fuel that is being added, right? That QR. So that is getting added, right? So that is QR. Okay, right. So now these many information has been given, and also two more information is given. The enthalpy of the gas that is getting in, HA, is given, and the enthalpy of that is going out, HJ, is given. Now CJ is being asked. Okay, now let's do one thing. As a next step, let's apply the steady flow energy equation. So the steady flow energy equation is called as SFE, right? Let's apply the steady flow energy equation across this volume, control volume, from inlet to exit. So if you apply the steady flow energy equation as we studied in the class, m dot A is equal to HI plus of CA square plus 0, because of this hiding thing, minus QL, because the energy is getting lost here, right? So it's minus QL, and then plus the amount of fuel that is getting m dot F into QR, fuel heating value, which is equal to, so this entire term is equal to m dot A plus m dot F. So that is the total mass flow rate into HE plus of CJ square. So now if you see in this equation, we know almost everything except CJ. HI we know, CA we know, QL we know, M dot F, QR that we can calculate. M dot F by M dot A is given, right? So from there we can calculate that easily. And then HE is also known. The only unknown is CJ. So let's do that CJ calculation here. So let's rewrite the steady flow energy equation in a convenient form now. HI plus of CA square minus QL by M dot A plus M dot F by M dot A into QR, which is equal to 1 plus M dot F by M dot A into HE plus of CJ square, right? So now this is very straightforward, right? I just have taken M dot A from the right hand side and divided that in the left hand side. And if you see the question, the heat law has been given per kg. So just nothing but divided by mass flow rate. So instead of QL by M dot A, we can directly substitute 25 kilojoule per kg. Okay, now let's substitute all the values here. So this has been given as 260 into 10 to the power 3 plus half into 270 square, which is the CJ value, minus I think QL is 25 into 10 to the power 3. So this is not just QL. QL divided by M dot A is 25 into 10 to the power 3 because it is given in terms of per kg. M dot F is divided by M dot A is given 0.019 if I'm not wrong, into QR. QR is already correctly given 44.5, but it's megajoule, so 10 to the power 6. So that information is also given, which is equal to 1 plus 0.019 into HE is given, right? So HE is 912 into 10 to the power 3, that's HE, plus half into CJ square. So in this equation now we know everything except CJ. If you solve this equation mathematically, you will get CJ is equal to 583.08 meter per second. So the solution, the exit velocity that is coming out of the nozzle is 583.08 meter per second. So let's move on to the next problem. This is a relatively very easy problem. It's a straightforward problem. So how does the propulsion efficiency of a turbofan engine operating at a given Mach number? So your Mach number is fixed, your inlet velocity and the Mach number is fixed, and a given altitude. So your altitude is also fixed, will change with respect to the increase in compressor pressure ratio. So this is coming from a straightforward equation that we know. So the graph is very simple. So the relationship one, if you do the ideal cycle analysis of a turbofan engine, we will get the chart between the compressor pressure ratio, which is pi c, and the propulsive efficiency eta p. So for a given Mach number, for a given altitude, if the compressor pressure ratio increases, your propulsive efficiency will come down. So this is how the chart looks like. Okay, this is for a ideal turbofan engine. So from here you can directly write it decreases, right, as you increase the pi c, which is the compressor pressure ratio. So as pi c increases, eta p, which is nothing but your propulsion efficiency, decreases. So that decreases monotonically is the right answer. Let's move to the next question. The combustion process in a turbo shaft engine during ideal operation is. So in a turbo shaft engine, the combustion process during ideal operation is, the combustion process is always isobaric, which means that there won't be any pressure drop or pressure increase, because always compression will happen at high pressure, but in an ideal pressure a combustion process there won't be any pressure drop or pressure increase. So the combustion process here will be isobaric. Okay, so that's the physics that we'll assume when we get into ideal combustion process. So now let's move on to the fourth question. Hot gases are generated at a temperature of 210 200 2100 Kelvin. So first let's write, as usual, let's write all the given information here. Okay, so the given information is the temperature is 200 and 2100 Kelvin. So T infinity is given as 2100 Kelvin. Okay, the hot gas is generated, and the pressure is also given. So P infinity is given as 14 megapascal. Okay, 14 mega in a rocket chamber. So P infinity and T infinity has been given to you. Now hot gases are expanded ideally to the ambient pressure, which means what? P exit is equal to PA, because it's ideally expanded, which means that when the exit pressure of the nozzle will be equal to the ambient pressure, which is equal to 0.1 megapascal. Okay, this is because of ideal expansion. Okay, if it's not ideal expansion, then PE will not be equal to PA, since it is given ideal expansion. Okay, and the throat area A star has been given as 0.1 meter square. The molecular mass of the gas is 22 kg per kilomole. So the molecular mass M is equal to 22 kg per kilomole. The ratio of specific heat, so gamma is given. So you cannot use the gamma of air, right? It is gas. The gamma of air is 1.4, so you have to use gamma of gas here, so which is 1.32, which is given in the question. And the universal gas constant R naught is given to be 8314 joule per kilomole Kelvin. That's good. The acceleration due to gravity is also given, which is G is equal to 9.8 meter per second square. So they asked what is the specific impulse of the rocket. So it is very clearly they have asked what is the specific impulse of the rocket. So now let's start with the formula for specific impulse. So what is this formula for specific impulse? ISP is equal to, as studied, F, which is a thrust divided by weight, right? Weight flow rate of the propellant. So W dot P. So which is nothing but weight flow rate of the propellant. And F can be written as M dot P, mass flow rate of propellant. Because it's a rocket engine, it's only M dot P. It's not M dot A. There is no gas, right? M dot P into C. C stands for the exit velocity, divided by here M dot P into G. G is nothing but acceleration due to gravity. M dot P is nothing but mass. So that you'll get weight. So if you do that, both things will get cancelled. So CE by G will give you the ISP. CE is nothing but exit velocity of the jet, the gas that is coming out of the nozzle. So now we have to find what is this CE, right? If we can able to find what is the CE, then we could able to easily solve what is the ISP, right? Let's see how to find out this CE. Okay, so let's move on to the next slide. From the rocket equations, we know that the CE expression is C is equal to root of 2Cp into T infinity into 1 minus Pe by P infinity, the whole power gamma minus 1 by gamma, right? Then If you find out what is the CP and this, the CE divided by G will give you the specific impulse. So let's figure out how to find out that. 2 into CP, you cannot substitute the CP of the air. We have to calculate the CP and substitute. So let's calculate the CP here. Okay, because for gases, CP will be different. CP minus CV is equal to R, that we all know. And CP minus Cp by gamma is equal to R, because we know that Cv is equal to Cp by gamma, right? Because Cp by Cv is equal to gamma, right? So now if you take Cp out commonly, 1 minus 1 by gamma equal to R. Sorry, this R. Now Cp is equal to gamma R by gamma minus 1, and Cp is equal to gamma has been given as 1.32. That's what is given in the question, right? You should not use 4, okay? Into R has been given as, value of the R is also given in the question. So if you substitute the value of R here, divided by gamma minus 1 is nothing but 0.32. R value is also given in the question. You will get your Cp to be 1558.875. 875 joule per kg Kelvin. So, ideally the Cp of the air is, it's very easy, right? Generally the Cp of air is, as we have studied, 1005, right? Generally, but you should not use this value. Now you see, because of it's a hot gas, it is 1558. So there's a difference of 500 units. So keep that in mind. Okay, don't substitute our normal air Cp, then your answers will be wrong. So I hope you all know how to substitute this R, right? Don't substitute the R that is directly given in the question. R, this whatever is given in the question is universal gas constant. This is a local gas constant. So R is equal to universal gas constant R naught divided by molecular weight. So both of them has been given in the question. What is R naught? It is 8314 divided by molecular weight. Molecular weight is also given of the gas, right? I think it's 22. So if you substitute 8314 divided by 22, that is your R. Substitute that R here. Okay, don't substitute the universal gas constant. That R is different. That is universal gas constant. This is local gas constant. So universal gas constant divided by its molecular weight will give you the local gas constant. So you have to substitute that, then you will get the Cp to be 1558.875. So now we have got the Cp 1558.875 into T infinity, which is already given in the question. I think it's 2100. Yes, Kelvin. And 1 minus P infinity is also given, right? P infinity is given. P is like ambient ideally expanded. So it is 0.1, and P infinity is given to be 14. I think both of them are in megapascal. So into 10 to the power 6 will get cancels. The whole power gamma by gamma minus 1, which is nothing but 0.3.2 divided by 1.32. Okay, 0.32 divided by 1.32. Now I rewrite this equation. Now everything in this equation, 2 into 1558.875 into 2100, which is T infinity, into 1 minus 0.1 divided by 14, the whole power 0.32 divided by 1.32. So CE, what is specific impulse? CE ISP is equal to CE divided by G. That we have seen in the formula, right? If you see here, right? Specific impulse is nothing but thrust divided by weight flow rate. If you substitute the value of thrust and weight flow rate, you will get CE by G. G value is also given, which is 9.8. So now specific impulse is nothing but CE divided by G. So this entire equation 1 divided by 9.81. This will give you the ISP. And if you solve this, substitute the mathematical value, and then you will get the value to be 218.17 seconds. Okay, so that's the specific impulse of this particular problem. So the answer is 218.17 seconds. So moving on to the next question. At a design condition, the velocity triangle at a mean radius of a single stage axial compressor, okay, is such that the blade angle at the rotor exit is equal to the 30 degrees. The absolute velocities at the rotor inlet and the exit are equal to 140 meter per second and 240 meter per second respectively. So what they have given? They have given first information they have given us beta 2, right? Beta 2 is equal to 30 degrees. So in the diagram also they have clearly given. So this is the axial direction, and W2, the angle between the W2 and the axial velocity is beta 2, which they have clearly given 30 degrees. And again they have given the absolute velocities of rotor inlet and exit. So C1 and C2, absolute velocity are nothing but C1. C1 is equal to 140 meter per second and C2 is equal to 240 meter per second. Now again, V1 also given. The flow velocity relative to the rotor at the inlet and exit are, so V1 is 240 meter per second and V2 is equal to 140 meters per second. But if you see here, what is C1 is equal to V2 and C2 is equal to V1, which means what? If you see this, it's a symmetrical triangle, right? It is symmetric velocity triangles. So both the velocity triangles are same. It's a symmetric velocity triangle. Okay. So now when it becomes a symmetrical velocity triangle, right, then it's very obvious from this diagram. It is very obvious that, so this is your beta 2, which is 30 degree, and this is your alpha 2, right? And if I draw a line like this is your beta 1 and this is your alpha 1, beta 1 and alpha 1. Okay, since it is a symmetric velocity triangle, we know that C1 cos alpha 1, from the diagram only we can directly write C1 cos alpha 1 is equal to V1 cos beta 1. So from here, if you substitute, what is C1, which is given 140? 140 into cos 30 degrees, because your beta, since it is a symmetric triangle, your beta 2 has to be equal to alpha 1. So your beta 2 is equal to alpha 1. Okay, 140 cos 30 degrees is equal to, if you see this diagram, right, this value has to be equal to beta 2, this 30 degree, which is equal to V1 is nothing but 240 into cos beta 1. Beta 1 we don't know. So from this expression, we can easily calculate beta 1 is equal to 59.66 degrees. So first we have identified what is beta 1. So since we know the beta 1, now let's apply the formula of the rotor speed by just using the velocity relationship. If you see this, we have to find the rotor speed, right? Rotor speed is nothing but u. So u is asked in the question, right? So it's very straightforward that u is equal to c1 sine alpha 1 plus v1 sine beta 1. So c1 we know, alpha 1 we know, v1 we know, beta 1 we know. Beta 1 we just calculated. So 140 sine 30 plus 240 sine beta 1 we just calculated, which is 59.66 degrees. This will give you the value of rotor speed or the blade speed u. U is equal to 277.13 meter per second. So the rotor speed is 277 0.13 meter per second. Now let's move on to the next question. So the air flow rate through the gas generator of a turboprop engine is 100 kilograms per second. So there is a turboprop engine and they are giving that m dot a mass flow rate is given to be 100. The stagnation temperature at inlet and exit of the combustor are. So they are given what is the stagnation temperature inlet and exit of the combustion has been given, which is 600 Kelvin, and after combustion obviously we know the heat will go up because of the addition of fuel. So let's try to understand this in a schematic way or a diagrammatic way. So this is, let's assume this is the compressor and combustion chamber, and this is m dot a, which is equal to 100 kilogram per second, and the inlet temperature of the combustor is, let's put T01, which is equal to 600 Kelvin, and the exit of the combustion is T02, which is equal to 1200 Kelvin. Okay, so they have given the burner efficiency to be 90%. So eta B, which is nothing but burner efficiency, is equal to 90% they have given. And they also told that the heating value of the fuel, which is nothing but Q, heating value is nothing but QR. Okay, the QR, the heating value of the fuel, which is getting added, right? In the combustion, you'll add heat, the fuel, right? That value is 40 megajoule per kg. Okay, and they have given the value of CP. The CP is 1000. Okay, they have given the value for air, it's 1000. For gas, after it get combustion is done, right? It becomes gas. That CP is 1200. Okay, so how we have to write is the air that is coming in, which is CPA, which is 1000 joule per kg Kelvin. The air that is coming out, which is gas, because as soon as you add fuel, it will become gas. CPG is equal to 1200 joule per kg Kelvin. The flow rate of the fuel being used is, so they have just asked what is the m dot f to balance this equilibrium. What is the m dot f? What is the, so m dot f will be given here, right? So what is the value of that? So it's a combustion process. Inlet mass flow rate is given, inlet temperature is given, inlet CP is given, burner efficiency is 90%, and what is the fuel heating value, that is also given. Exit temperature, exit gas CP is also given. They are just asking what is the amount of fuel that has been added. So now let's apply the again the steady flow energy equation between this. So it's m dot a CPA, which is nothing but A stands for gas, air, into T01, which is nothing but your enthalpy, right, at the inlet, plus eta B, efficiency of the burner, into m dot of the amount of heat that fuel that is getting added, into QR. QR is nothing but the fuel heating value, which is equal to m dot A plus m dot F, because once the gas mass flow rate will be m dot A plus m dot F into CPG into T02. Now in this equation, everything is known. M dot A, CPA, T01, eta B, QR, except m dot F, everything is known in this equation. Now if you substitute the values here, and if you find out what is the value of m dot F, so that's very simple. Let's get the expression of m dot F from that equation. CPG into T02 minus CPA into T01 into m dot A divided by eta B QR minus CPG T02. And if you substitute the values here, CPG is 1200 into T02 is also 1200 minus CPA is 1000 into T01. What is T01? T01 is 600. That is also given. T01 is nothing but the inlet temperature of the combustor. Okay. Into m dot A. M dot A is given to be 100 kilogram per second divided by eta burner is nothing but 90. So it will become 0.9 into QR is 40 megajoules, so into 10 to the power 6 minus CPG is again 1200 into 1200 T02. This is your m dot f, and if you calculate the value, it will come out to be 2.43 kilogram per second. So this is the amount of fuel that is being burnt per second. So the answer is 2.43. Okay. With this, let's move on to the next question. A solid propellant rocket producing 25 meganewton thrust. A solid propellant rocket is producing 25 meganewton thrust is fired for 150 seconds. So the time here is 150 seconds. Okay. The specific impulse of the rocket is given, which is 2980 ns per kg. Okay. Now, how much propellant is burned during this operation? So during this time of operation of 150 seconds, that rocket has produced 25 meganewton, and the specific impulse of the rocket is given. Then to produce this much newton around 150 seconds, which for the rocket which is having 2980 specific impulse, how much propellant you have to burn, the amount of propellant that has been burned. So let's, as usual, let's write in the given information. So F is equal to 25 meganewton and T is equal to 150 seconds, and ISP is given equal to 2980 Newton second per kg. So now let's first write what is the specific thrust for this particular operation. So they have given only thrust. Let's calculate what is specific thrust. Fs is equal to thrust divided by m dot p, mass flow rate of propellant, that we all know. So F divided by mp, mass of propellant, because that's what we need to find out, right? They asked what is the, how much propellant is burnt. So how much mass of the propellant is burnt, that's what we need to find out. Mp is fine. Mp we have to find out, divided by T. So this is nothing but mass flow rate. M dot P is nothing but mp divided by T. So if you, we have to only find out this, correct? So m, from this equation we can get easily that mp is equal to F thrust into time divided by specific thrust, right? Yes. So which is equal to, what is specific thrust? 25 into 10 to the power 6 mega thrust, they are told, right? Time is also given into 150 divided by specific thrust. So what is specific thrust in this case? The specific thrust is nothing but ISP. Okay, because if you see Newton second per kg, right? The specific impulse 2980. So if you equate that, so that is nothing but your specific thrust. If you see the equation, the units, right? Ns per kg is nothing but the specific thrust. So if you substitute 2980 here, you will get the answer to be 1.26 into 10 to the power of 6 kg. So the answer is option A, which is 1.26 into 10 to the power of 6 kg of propellant has been burned to produce 25 meganewton of thrust for a period of 150 seconds. Here you have to be very careful here. They are given specificals in the form of different unit. Okay, so this is nothing but your specific thrust, specific impulse. Okay. So let's move on to the next question. So it's again a turbine question. A single stage axial turbine has a mean blade speed, so which is nothing but the U blade speed has been given. So first let's write all the given information. U is equal to 340 meter per second at a design condition with the blade angles at the inlet and exit rotor. So they have given the blade angles, which is nothing but beta 1 and beta 2. So beta 1 is 21 degrees Celsius and beta 2 is 55 degrees Celsius. Okay. Then they have also given the degree of reaction at the mean radius of the rotor. So the degree of reaction they have given it to be 0.4. So now they have given the annulus area at the inlet. So they have given the area at the inlet. AI is equal to 0.08 meter square. And the density of the gas at the rotor inlet is. So they have given the density of the gas at inlet. Rho I is equal to 0.9 kilogram per meter cube. Now they are asking the flow rate through the turbine at these conditions. They are asking mass flow rate m dot. Okay. So they are asking what is m dot I. So this is what is asked. So since the degree of reaction is given, let's start with the degree of reaction. We know the degree of reaction is equal to CA, which is the axial velocity, divided by 2U into tan beta 1 plus tan beta 2. In this we know beta 1, beta 2, U we know what is that next. Degree of reaction we know. From here we can calculate what is the axial velocity CA. So let's substitute the value of CA we don't know, divided by 2 into 340 into tan 21 degree plus tan 55 degree, and degree of reaction 0.4, so which is nothing but equal to 0.4. From here if you calculate what is the axial velocity CA will come out to be 150.11 meter per second. So now that we have calculated CA, then it is very straightforward, right? So because what they have asked, what is the mass flow rate at the inlet of the turbine? So what is mass flow rate formula? M dot I is equal to AI rho I into CA. So m dot I is equal to, what is AI? 0.08, rho A is 0.9, CA we just calculated using the degree of reaction formula. So which is 150.11. So if you calculate this value, m dot I is equal to mass flow rate at the inlet is 10.81 kilogram per second. So the flow rate through the turbine at these conditions 10.81 kilogram per second. So then moving ahead to the next question, how does the specific thrust of a turbojet engine change for a given flight speed with increase in flight altitude? So which is very easy question. So what is specific thrust? Fs is equal to Vj minus Vi, because generally the thrust formula is m dot I divided by what is specific thrust, which is nothing but thrust divided by the mass flow rate. So what is thrust? M dot into Vj minus Vi divided by m dot I. So m dot I will get cancelled. So this is specific thrust. So as we all know that if you plot this thing, right, as for a given inlet velocity, so we have to fix this because they have given for a given flight speed. So they have freezed your Vi. So there is no change in Vi, but as altitude increases, what will happen? Vj will come down. So as altitude increases, Vj will come down because of less mass flow we get, because rho will come down. As altitude increases, density will come down. So we'll get very less mass flow rate. So the energy momentum of the hot gases will be less. So the expansion that will happen through the turbine and the nozzle, that will be also be less compared to the higher momentum. So Vj will come down. So what will happen as altitude h increases, your Vj will come down. Hence your Fs, specific thrust, will also come down. Okay, so the answer is the specific thrust will decrease monotonically. Okay, so with this, the solution for the propulsion questions are done. Let's see some other solutions in the next video. Thank you.
If you like this video, please Like, share and subscribe my channel to encourage me. Thank you.